Hello, my name is Shweta, and I'm a professor in the computer science department at IIT Madras. I work in the area of cryptography with a particular focus on post quantum cryptography. So, let me tell you a little bit about that. First, let's just begin with what is cryptography. And this, as you might know, is the art of secret keeping with rigorous mathematical guarantees. And what is the kind of guarantee that we might give? Well, cryptography guarantees that breaking a crypto system is at least as hard as solving some difficult mathematical problem. And how do we give such a guarantee? By means of a reduction, being computer scientists, right? So assuming that there is an attacker against my crypto system, I should be able to design a reduction which leverages this attacker in order to solve this hard problem, right? So this is the way in which we will prove that this crypto system is going to be secure as long as the underlying problem that we chose is a good one, a hard one, right? But when I say that the underlying problem is good or hard or difficult, right, what does this really mean formally? So in particular, difficult for who? And this so-called cryptographic adversary is typically modeled in computer science as a classical computer. Now, here, when I say computer, I really mean algorithm because, well, the computer has to run some algorithm, right? And the guarantee that we can give is that unless the attacker actually solves this hard problem, just guessing or brute force trying out all approaches would take like a very, very long time. Let's say more than the age of the universe, even. Okay. And moreover, this guarantee is robust to the type of computer you use. So it doesn't really matter if you change the quantity of your underlying computing resource because this is an asymptotic style guarantee. However, things become very interesting if you change not the quantity, but the quality of your underlying computing resource. So, in particular, if instead of classical algorithms, you allow attackers to be quantum algorithms, then the whole picture changes. Okay, so what is a quantum algorithm? Well, this is a fundamentally new paradigm of computing. And essentially, what that means is that now, instead of using the laws of classical physics, we're going to use the laws of quantum physics. And this can allow the transformation of your memory in your computer into a quantum superposition of all possible classical states. If you don't know this term quantum superposition, don't worry about it. What it basically means is that, in a classical world, a bit is either 0 or 1. But in a quantum world, a bit, a qubit, a quantum bit as it's called, is both 0 and 1 with some probability. Okay, so with some probability 0, with the remaining probability it's 1. And now if I have an n-bit register, this can potentially store up to 2 to the n values, right? So this could allow exponential speedups. Now, it's not true that it will always allow exponential speedups, but in some cases it can. And unfortunately, all the popular hard problems that we use to build cryptography in present day all get broken if you ask a quantum algorithm to solve them. Okay, so unfortunately, these problems lie in the territory where exponential speedups using quantum algorithms are possible. So you might well ask, is this threat real or is it, just in theory? And the short answer is yes. So yes, the threat is real, and it's not that we already have quantum computers that can break all present-day cryptography. So today we still think that our codes are secure, but there have been a lot of strides in developing sort of better and better quantum computers. And we expect that in the future these will exist. Okay, so we've already in the world started a process of standardizing post-quantum cryptography, and that is the kind of research that we're involved in. So what is post-quantum cryptography? As you might guess, you want to choose mathematical problems on which to base cryptography, for which even quantum computers offer no advantage. And one very promising candidate here is, lattice-based cryptography. So this is a lattice. Of course, this is not high dimensional. This is just dimension 2. And just to give you a taste of, the kind of hard problems we will be interested in, I'd like to show you one example. So this is the so-called shortest vector problem. It's a very famous problem. And what it says is, if I give you a high dimensional lattice, can you find the shortest non-zero vector in this lattice? And this turns out to be a very hard problem and also very expressive. So it turns out you can do some very interesting cryptography using this, using the hardness of this problem. And if you're interested to find out more, send us an email. Thank you.